This is section 8.3, part C, constructing a confidence interval for mu. When the conditions for inference are satisfied, the sampling distribution of x bar has roughly a normal distribution with a mean of mu and a standard deviation of the standard deviation for your population divided by the square root of your sample size. Because we don't know the standard deviation for the entire population, we estimate it from our sample standard deviation, or S sub x. So when we're doing this estimation, we then estimate the standard deviation to be the standard deviation of the population divided by the square root of n. This value is called the standard error of the sample mean x, or just the standard error of the mean. So to find your standard error of the sample mean x bar, you do the sample standard deviation divided by the square root of the sample size. To construct a confidence interval for mu, replace the standard deviation sigma divided by the square root of n with your standard error, which is S sub x divided by the square root of n, in the formula for a one sample z interval for the population mean. Use critical values from the t distribution, where you remember the degrees of freedom is equal to n minus 1, in place of that critical value z. So now, to find our interval, we're going to have our statistic plus or minus our critical value times the standard deviation of the statistic. Or we're going to have the x bar plus or minus the t star, so the critical value for a t distribution, times the standard deviation divided by the square root of n. This one sample t interval for a population mean is similar in both reasoning and computational detail for a one sample z interval for a population proportion from section 8.2. So we will now pay more attention to questions about using these methods in practice. So the one sample t interval for a population mean, you're going to choose a simple random sample of size n from the population having an unknown mean of mu. Our level C confidence interval for mu is going to be x bar plus or minus t star times the standard deviation of the sample divided by the square root of n, where t star is the critical value for the t sub n minus 1 distribution. Use this interval only when the population distribution is normal or your sample size is at least 30 and the population is at least 10 times as large as the sample. As before, we have to verify 3 important conditions before we estimate a population mean. When we do inference in practice, verify the conditions is often a bit more complicated. So remember those 3 conditions that you have to check. You need to make sure it's random, so the data comes from a random sample of size n for a population of interest or a randomized experiment. This condition is very important. Then you need to make sure that it's normal. So either the population has to have a normal distribution or your sample size must be at least 30. You also need to make sure that's independent. So the method for calculating confidence interval assumes that individuals are observed independently. To keep the calculations reasonably accurate, if we are doing this without replacement, you do have to check that 10% condition, which means your sample size is no more than 1/10 of the entire population. The following example shows you how to construct a confidence interval for a population mean when the sigma, or the standard deviation, is unknown. By now, you should recognize the 4-step process. Since you are expected to include these 4 steps whenever performing an inference, we will stop saying to follow the 4-step process in examples and in exercises. So anytime you have to make an inference, you need to assume from now on you do need to do that 4-step process. A manufacturer of high-resolution video terminals must control the tension of the mesh of fine wires that lies behind the screen of a viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent to the production process. Here are the tension readings from the random sample of 20 screens from a single day's production. Construct and interpret a 90% confidence interval for the mean tension mu of all screens produced on that day. So remember, on the 4-step process, the first thing you need to do is state. So we want to estimate the true mean tension of mu for all video terminals produced this day at a 90% confidence interval. Next, we need to do our plan. When you do your plan, you need to state what process you're going to use. So are you going to use a one sample Z interval or a one sample T interval? And then you need to check the conditions to make sure you can actually do the process. So that's where you're going to check random, normal, and independent. So for this one, we do not know the standard deviation for the entire population, so we are going to use a one sample T interval for mu. Now we're going to check our conditions. So we are told that the data is from a random sample of 20 screens from the population of all the screen productions. Since the sample is only 20, we must check whether it's reasonable to believe the population distribution is normal. So what you're going to do is you're going to graph this data. You can graph it as a dot plot like in part A, you can graph it in a box plot, or you can do a normal probability plot. Remember, on a normal probability plot, it's going to say that it's normal if it is pretty linear. It's not curved or anything like that, no skew outliers. In that box plot, it does look pretty normal. It is about symmetric. There are no huge outliers. There's no huge skewness. And from the dot plot, you can see there's no big outliers, no information that shows us great skewness. So we can say the normal probability plot shows roughly linear, and the box plot has no strong skewness or outliers. So these graphs give us no reason to doubt the normality of the population. Now we need to check for independence. So because we took a sample size without replacement, we do need to check that 10% condition. And we can assume that if we do our sample size is 20, if we multiply that by 10, that's going to give us 200 video terminals. We can assume that they've made at least 200 video terminals in one day. So next is the do. This is when you're going to do all of your actual calculations. So we used our calculator to find the mean and the standard deviation of those 20 screens. So they gave us the data for those 20 values. Remember, you can input all that data into your list one, and then you can use your calculator to generate the mean and the standard deviation. So the mean for our sample was 306.32, and our standard deviation, or S of x, is 36.21. We are going to use a t distribution. So remember, to find your degrees of freedom, you're going to do your n minus 1, which is going to leave us with 19. And we're doing a 90% confidence interval. So if we go to our t table, we're going to go to degrees of freedom of 19. We are going to go to 90%, and where those two cross is going to tell us our critical value, or our t star, which is 1.729. So to find our 90% confidence interval, remember, our formula says you're going to do the mean from your sample plus or minus your critical value for t times the standard deviation of your sample divided by the square root of n. Or in this case, 306.32 plus or minus that 1.729 times the standard deviation of our sample, which was 36.21, divided by the square root of 20, because they did take a sample size of 20. And that's going to leave us with an interval from 292.32 to 320.32. The last step is always to conclude, and that's just to bring it back into context. So we are 90% confident that the interval from 292.32 to 320.32 millivolts captures the true mean tension in the entire batch of video terminals produced that day. Now that we have calculated our first confidence interval for a population mean mu, it is time to make a simple observation. Inference for proportions use Z. Inference for means will use T. That's one reason why distinguishing categorical from quantitative variables is so important. When we use Table B to determine the correct value of T star for a given confidence interval, all we need to know are the confidence level C and the degrees of freedom. Unfortunately, Table B does not include every possible sample size. When the actual degrees of freedom do not appear in the table, use the greatest degrees of freedom available that is less than your desired degrees of freedom. This guarantees a wider confidence interval than we need to justify a given confidence level. Environmentalists government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxide. Researchers collected data on the nitrogen oxide levels in grams per mile for a random sample of 40 light-duty engines of the same type. The mean nitrogen oxide reading was 1.2675, and the standard deviation was 0.3332. Construct and interpret a 95% confidence interval for the mean amount of nitrous oxide emitted by the light-duty engines of this type. Again, because we are making some type of inference, we do need to do the 4-step process. So we're going to start with our state, and we want to estimate the true mean amount of mu of the NOx emitted by all light-duty engines of this type at a 95% confidence level. Next, you're going to come up with your plan. First, you're going to say what type of process you're going to do. Are you going to do a Z interval, a Z confidence level, a T interval, or a T confidence level? You have to pick what type you're going to do, and then you're going to check the conditions. So because this is a mean, we do not know the population standard deviation, we are going to do a one sample T interval for mu if the conditions are met. And then you actually do have to write out and check the conditions. So the data comes from a random sample of 40 engines from the population of light-duty engines of this type, so we can say that this is random. We don't know whether the population distribution is normal, but because our sample size is 40, and that's at least 30, we can be safe to go ahead and use our normal processes for the T procedures. We did not sample with replacement, so we do have to check that 10% condition, and we can assume 10 times 40, which is 400. We can assume there's at least 400 light-duty engines of this type in the entire country. Next is the do, where we do our calculations. So the formula for our one sample T interval, again, is x bar plus or minus T star times the standard deviation of the sample all over the square root of n. We were told that the sample of the 40 engines for the mean was 1.2675, and we were given our standard deviation. So we don't have to do those calculations, we can just plug those in. We also know that our degrees of freedom will be 40 minus 1, which is 39. And we know that we want a 95% confidence level. But if you look at your table B, we go from 40 to 30. So we do have to go to our degrees of freedom, or whatever the next value is less than that on the table. So we are going to have to use degrees of freedom of 30, and this will give us a wider interval than we actually need, but it's safer to go wider than to go too narrow. So this is going to give us a critical value, or a T-star value, of 2.042. So if we plug all this information into our equation, we're going to end up with an interval of 1.1599 to 1.3751. So again, for the conclusion, you just need to bring this all back together into context. And we are 95% confident that the interval from 1.1599 to 1.3751 grams per mile contains the true mean level of nitrogen oxides emitted from this type of light-duty engine. So for Part B, the Environmental Protection Agency sets a limit of 1.0 grams per mile for the NOx emissions. Are you convinced that this type of engine has a mean NOx level of 1.0 or less? Use your interval from Part A to support your answer. So our confidence interval from Part A was 1.1599 to 1.3751. And this tells us that any value between those two is a plausible mean for your nitrogen oxide levels for mu for this type of engine. Since the entire interval exceeds that 1.0 limit, it appears that this type of engine violates the EPA limits. As we noted earlier, a confidence interval gives us a range of plausible values for an unknown parameter. We can therefore use a confidence interval to determine whether a specific value of the parameter is reasonable, like the EPA's 1.0 limit in that last example. So let's check your understanding. Biologists studying the healing of skin wounds measures the rate at which new cells closed a cut made in the skin of an anesthetized newt. Here are the data from a random sample of 18 newts measured in micrometers per hour. We want to estimate the mean healing rate mu with a 95% confidence interval. So first, let's define our parameter of interest. The parameter we're interested in is the population mean of the healing rates of the newts. What inference method will you use? And then check to make sure the conditions are met before we do our procedure. So because we are looking for a mean and we do not know the population standard deviation, we are going to use a one sample t interval for mu. Now we have to check our conditions. So the description says the newts were randomly chosen, so our random condition is met. We do not know if the data is normal because the sample size is not at least 30, and we don't know anything about the entire population. So we do need to graph our data and make sure that it's roughly symmetric with no outliers and that there's no huge skewness. So if we make a graph or a histogram of our data, we can see that the histogram shows that the data are reasonably symmetric with no outliers, so we can go ahead and check off that normal condition. The last thing we need to check is the independence. We have data from 18 newts, and they did not select these with replacement, so we need to check the 10% condition. If we do 10 times 18, that would give us 180 newts, and so there's clearly at least 180 newts out there, so that independent part has been checked. Now we need to construct a 95% confidence interval for mu and show your method. So we said we're going to do that one sample t interval. So we're going to start by finding our t star value. Our degrees of freedom in this case, since there are 18 newts, you would do 18 minus 1, and you would get a degrees of freedom of 17. If you go to table B, or your t table, and you look at a degrees of freedom of 17 and go to the 95% confidence interval, you will see that your t star value should be 2.110. From the information that's given to us, we can put that into our calculator and find the mean for our sample and find the standard deviation for our sample, so we can plug this into our formula. And this is going to give us an interval from 21.527 to 29.807. So if we interpret this interval into context, we can say we are 95% confident that the interval from 21.527 to 29.807 micrometers per hour captures the true mean healing time for newts.